called the everything abandoned shift when you purchase the operating system. Okay, which is true actually. But sometimes somebody says the kernel itself only is a minimal, because nowadays we pursue the as small, as tiny as possible for that the operating system. However, we have the better definition of the operating system. An operating system is a program, anyway, it's a software that controls and coordinate the use of hardware resource among various computer programs for various users. You can see all the discussion that we had the last class. It's between the computer and user interface, right? Also, we have the very limited the computer resources. So for that hardware resource, we should be smart to use such a computer resource. So we need to control and coordinate. That's all the things for the operating system. For that, we divide into 3 groups of the computer system. One is the CPU processor, second part is the memory, and third part is the I/O. Okay, so throughout the semester, we will mainly talk about the operating system in terms of the process management. From the 3rd week, I think the week after, we will start. Then that is half of the operating system. Actually, that is true, because our operating system, our program, anything running on the computer is based on the process. Okay? Then second part will be the memory, and last part is the I/O management. So we will see some of the basic computing architecture, even though we discussed a lot of them, but we will see more in detail. That will help to understand the operating system itself. Without understanding computer architecture, it doesn't make sense to understand the software running on that hardware. So first, the bootstrap program. Can you remember that? So when we turn on the computer, what happened? First time, there is the BIOS program. BIOS program is it's a program, right? It's a small, tiny operating system. Okay. Then what's the main role of such a program? It checks all the device, I/O device, and any new device, whether device is working very well, check to send the signal and receive and check. Then finally, it will direct to the first, the program, kernel program. Okay, that is the bootstrap program. Okay. That is the job of the BIOS program, bootstrap program. Is usually reside on the read-only memory. Right now, it's on the EEPROM or the flash memory. Okay, sometimes it's called the firmware. Then this is the general view of our computer system. As you can see, it consists of the CPU and memory and other devices. They are connected by the bus. There are 3 types of bus: address bus, data bus, and the control bus. Okay. By the way, you can see something. Disk is not directly connected to the bus. Instead, we have disk controller. The other is the USB-based device connected to the USB controller. And monitor is graphic editor. What are they? Controller or the adapter? What? These are the. It has driver. Okay? Which means, in terms of computer, CPU or memory, this computer, they don't know what is this device and this device, this device. Each one has the different input and output. Mostly it's the input and output signal data. Okay? Even though they are standardized, each one has a different one. So we need something in the middle. to connect such a device into the computer. So that is a disk controller. Disk controller has the device program. Okay, that program can convert the I/O signal to the something computer signal that can be understood by your computer. That was the reason long time ago when you purchased a new I/O device such as the hard disk drive. That hard disk drive actually include small diskette or program, so you need to install that program. Then finally, your operating system understand the signal from the new device. Nowadays, you don't have to. Why? Most of them are already included in your operating system itself, or sometimes it can plug in, right? Which means when you plug in, when you connect, automatically download such a new the program or device program through the internet, then install automatically. So sometimes you may not realize such as installing the device program. That is the controller. Okay. Such a device, okay. So each device controller has a local buffer. Buffer will be used for the temporary storage to send the signal from I/O devices to the computer. The computer means the CPU, or vice versa. So that is the I/O, the local buffer. So then, how do you communicate? How does the I/O device communicate with the computer? That means the CPU. So for example, the CPU would like to read the data, then send the request to the disk controller. Then this controller read the data, so using sector number, cylinder number, and so on. Then finally find the data, and before you return such a data to the CPU, there is stored at the local buffer. Then you just send such a data to the CPU. No, instead you need to inform to your CPU, I'm ready to return your requested data. That is called the interrupt. Okay, you probably heard about the interrupt. So nowadays, our computer system, any computer system, my laptop, your laptop, any computer, is an interrupt-driven computing system. At that time, what does that mean? Interrupt. Interrupt means. So if you do not turn off the cell phone, that interrupt me. Right? So stop something, then I cannot continue my study. I need to check my cell phone. Mine mostly it's the ring at the beginning of the semester, mostly not. Anyway, that's the interrupt. That's the same thing. If you send back the data to the CPU, you need to first interrupt, because the CPU are most the busiest device. So they are doing something. CPU is doing something. So you need to interrupt. You need to stop your job. Then please listen to me. Then once that CPU is stopped, then you can send back. You can send back the data to your CPU. Other device is the same thing. Even CPU can interrupt the I/O device once it's too busy. Then the request the job. So that is an interrupt. So nowadays the modern computing system is interrupt-driven. The computer system or interrupt-driven operating system. We will see a little bit more about the interrupt. Okay. So when you learn your microprocessor, you probably learned about some instruction like the INT. Something number 9, 21, 26, something like that. Do you remember that? No? Yes? Yes, that is interrupt. What does that mean? That when you learn this one, what happened? Stop. Actually, this instruction called between the function in your operating system. Okay? In your operating system, your operating system includes some procedure. For example, read the data or display the data, okay? Where? In the memory, at the beginning part, 64K part, it has interrupt 1, interrupt 2, interrupt 3, and which is called interrupt vector. So all your I/O, input and I/O are stored in this interrupt vector. Okay, through the interrupt vector, so you can actually access your I/O device. Each operating system has their own list of interrupt vector. Okay, so using instruction, you can actually code such a interrupt vector, so you can read the data, you can display the data, sometimes you can write the data, you can actually use the speaker, or you can print out your data. So that is the interrupt vector. Okay, so there is another types of interrupt, that is trap and exception. What is a trap? What is the exception? I think that you heard about the exception. Where? In your Java program. Yeah. It's the same thing. So why don't you think about the trap? Trap is quite similar as the exception. So you actually put this amount of the exception. So just in case something happened, do something. Right? It's the same idea. So trap and the exception are the software generated interrupt. Mostly when we are saying the interrupt is the hardware between I/O devices and the CPU. So in the hardware, you can send a signal. I'd like to stop, interrupt, I'd like to use that one. I'd like to return your requested data. However, sometimes you can do the same job from the program. Sometimes it's called trap, sometimes it's exception. So like the trap is mostly system-wide. Exception is user-defined. Okay? What kind of the system? The system exception. For example, divide by 0. Divide by 0 is a serious problem in computer. Why? No way to keep the infinite number. Okay? If you try to do something, it's forever. So you need to stop. Okay? You need to send a warning to computer, your CPU. At the time, you can, in case divide by 0, it's kind of a trap, it's kind of an exception. So, in case something happens, in case the divide by 0, you can stop and send the signal to your CPU. Somebody would like to divide by 0, then we'll handle such a problem. That is the trap and exception. It's a software driven the interrupt. The others are hardware-driven interrupt. So, how can we handle the interrupt, which is based on the polling or vector? I already explained about the vector interrupt system. It's already listed the beginning of the memory as a vector. The interrupt 1, interrupt 2, interrupt 3, something like that. You can just code that vector using the instruction, then you can use the interrupt. Or the polling means, what is a polling? Polling is you don't know when it is available or not. You can just keep checking forever until it's okay. So that is called the polling. So interrupt is based on such a polling mechanism. You are not going to wait just somebody info. Instead, you just check, keep checking. That is the polling.
Keep checking what?
Checking the whether interrupt is available. Okay. So for example, okay, so this is the definition of the interrupt and trap that I introduced. So definition is it can be either software or hardware, the mechanism for what? To send the signal, basically. Okay, use the signal for occurrence of an event. Depending on the event, it can be different kinds of the interrupt and the trap. Okay, so I already explained about what is the trap and what is the software interrupt. Okay. Then what happens when we interrupt? Okay. So for example, when you interrupt, so first, when the event happens, for example, you can consider the divided by 0 or something other event, or whether there is the output from the I/O device, then I/O controller has the data in the local buffer, then that is an event. Then should interrupt. So then CPU is interrupted. Then at that time, CPU is stop current process. What does it mean? CPU stop and stop the current process. This is a time. Let's say this is a CPU time. CPU is learning. How many CPU do you have? Let's say we have one CPU. Anyway, it's true. At certain time, CPU can execute only one process, no matter how many processes are running. But why don't you check your laptop or computer or the cell phone? How many processes are running? So many processes. What does that mean? Is it true? So many processes are active at the same time? No, only one of them will take the CPU resource. So currently only one process, but in case something event, there is that event sender interrupt to the CPU, then CPU is a stop. Should be stop. Okay? That time CPU should keep checking, following that interrupt. Once it's CPU is stop, then you need to, we will see later in maybe chapter 5 or 6, that is called a context switch. Context switch means probably this CPU has many information in register, AX, BX, CX, and IP, a lot of information, and something information about the memory and current instruction, everything, current status, you need to save. Okay? So also, one more thing is, once you receive the interrupt, you need to stop, disable the interrupt. Because it can be interrupt again. Somebody, the other device or event will interrupt. So, block. You are not going to check the polling. So you are not going to do the poll to check the interrupt. It's a block, disable, and save the current status, okay, and bring up the other process that caused this interrupt. Okay, probably another process will ask before to read this data or that caused this event. You need to bring that information to the CPU. Okay, that is called the context switch. After context switch, then you can enable the other interrupt, then continue this process. That is the basic mechanism in operating system. Okay, any operating system which is based on the interrupt, then that followed this one. Okay.
So, what exactly the context switch do?
Context switch, I will explain details later. This context switch is the switch all the information about the CPU with other process. That process caused this interrupt. Okay, for example, process A currently requests I/O. So interrupt an I/O controller, then this controller will read the data, right? By that time, there's nothing CPU can do. Then CPU switch into the other process to maximize the CPU time. So this is a process A, but this time process B. While process B is running, this one is done. Then you can interrupt the CPU. Then this interrupt is caused by process A. So you can bring the process A into the CPU. So this, from now on, this is a process A. This one is called context switch. Okay, you switch the context of the CPU. we will see details later. This is just an overview of the operating system architecture, okay, for better understanding. Okay. Then we have the I/O. Okay. In the I/O, we can see I think that this one may be okay. So we will see the details of the I/O structure in the chapters 10, 11, and 12 at that time. Okay? And another part of the I/O is the storage structure. Storage, actually, the hierarchy. What is the smallest but fastest storage in the computer system?
ROM.
It's a
ROM.
register. Okay? Register is always the fastest. That's the only storage that CPU directly access the data. However, it's not enough, right? It has only AX, BX, CX, DX. I cannot remember all of them, but it's very limited. So you need to access memory, okay? This one. So we have the memory. Because of that, during your assembly language class or the microprocessor class, you learned a lot addressing. Because the memory itself is nothing but address, okay? So between register and memory, you can bring in and out the data. Because main memory itself is much bigger than the register, CPU. The problem, this is so fast. Register, how often? When you read the data, there's no time, even almost. When you read the data from register, it's nothing. Okay, so very fast. But memory, you need to go through the bus. It takes a time, 700 to 800 nanoseconds, something like that, which I cannot remember exact number. Okay, but it takes a time. To reduce such a time gap, we can use
Cache.
that time, that is a cache. Then, now I have a question. What is the difference between cache and buffer? We have cache, we have buffer. What is the difference? It's quite similar, but different. Faster? Which one is faster? Cache?
Cache is kind of a permanent non-volatile storage, while buffer is volatile storage.
Buffer is what? One?
Volatile, so I mean, cache we can save the memory permanently. Buffer
Save the memory, yes. What about the buffer?
Buffer is just temporary.
Where can you find the buffer easily? If you drive highway, if you exit or guard lane, you can see the buffer, just in case accident. You don't know buffer? It's a yellow stuff, or it has something sand or the water inside. What's the main role of that buffer? Because your word is not moved, okay? So it's a zero, the velocity. Your car is 100 miles per hour. Okay? If you hit directly, you will be dying. So because to reduce the gap, speed gap between your car and your world, 100 and the zero, there might be buffer to reduce it. Similarly, we can use the buffer in when you watch the video stream. If you have the very low bandwidth, the network, you can see the something buffering. What does it mean? So in case the speed gap, we can use the temporary space to keep the data, okay? Then sometimes we may not realize such a speed gap. That is buffer. On the other hand, cache is what? For recycle. To speed up, to access the data very fast. So, even main memory is kind of cache between CPU register and hard disk drive. Hard disk drive is too slow, so why don't we keep the faster device, faster media, okay, such a data in this data in the memory. Then instead of access the data directly hard disk drive, we can access data to the memory, which is faster, right? What if you cannot find the data from the memory? Anyway, you need to access a hard disk drive. Otherwise, most of the time you can get data from the memory. Okay? Then you can speed up. That is a cache. It's a recycling data to access the data very fast. Okay? Similarly, even main memory is not fast enough. We can put the cache in between CPU and memory, depending on the layer. L2 cache, L4 cache, layer 2, layer 4. So it doesn't have to be very large. If you have the very large cache memory, it takes some time to find the data, to manage the data, even from the memory, and even from the L2 cache and L4 cache. So that is a cache. So if we have the hard disk drive, we have the finally magnetic tape. Here, what is the benefit? What is benefit of this one? Speed. Problem? Small and expensive. So least expensive, cheap medium. So still magnetic tapes are used for back up the data. Okay? This is usually linear, sequential access still, but still used. So this is the diagram to understand such a storage hierarchy. So when you consider such a storage, you need to consider speed and cost. These two are the race dilemma. Which one you are going to consider, speed or cost? Okay? If we have very cheap memory, then I think that we can replace all hard disk drive by such a memory base, like our cell phone. That is the reason, even though this is a small but very expensive than my laptop, because it used the memory for your hard disk drive. Okay, this one actually it has the hard disk drive. It's cheaper but larger. Okay, bigger size. So always, this is the dilemma. At that time, we can address the problem of the speed using the cache. Okay? And also each device should have the should be connected to the device driver, this controller, okay, that can understand the input and output signal. Okay. So we already explained about that. And nowadays, solid-state disk SSD is more popular, which is memory, but it's non-volatile. Okay, volatile means if there is no power, you lose the data. But this one, solid-state disk is non-volatile, even though there's no power, you may not lose the data. Okay, so nowadays, this solid-state disk are more popular than traditional the hard disk drive.
But the hard disk is also non-volatile.
Yes, hard disk is non-volatile. So I already explained about the caching. Caching is the technique to reduce the speed again. Okay? But the buffer is used for reduce the gap between different bandwidths. Okay? It's a temporary space. Also, another thing we will see throughout the semester is the direct memory access structure. As I already explained, this is a good example. So in case there is an I/O, like in your instruction, switch of instruction, you need to read the data from the program or the specific file. Then you need to access the hard disk drive. At the time, during the I/O, anyway, CPU cannot proceed the next instruction. It's the I/O wait. You need to wait. It's a waste of the CPU time. So to address that one, we can context switch at the time. Then once this one read the data, this controller read the data, this controller interrupt the CPU, then send the data back to the CPU. When you read the large amount of data at certain time, contact the CPU and return, contact, return, contact, return. When you return this data, it will be stored at the memory. Don't you feel any problem? Whenever you read the data from hard disk drive, the memory, CPU need to invert to read the data. Mostly when you read a large amount of data, it's a sequential, so we don't have to contact each time the CPU. Instead, why don't we? From once it starts to read the data until the finish the reading, why don't we directly send the data from hard disk drive to the memory? That is called direct memory access. So which increase the performance of the CPU a lot. Okay, so instead of the interrupt the CPU whenever we read the data, we can send the data from the I/O device to the memory. That is the direct DMA. So nowadays, most of the operating system use such a DMA structure. You can see the example of the DMA from this slide. So this is a CPU, this is a memory, this is any device, I/O device. Let's say that this is the hard disk drive. So whenever you read the data, you need to request the I/O. Okay. Then return the data, interrupt, then return the data. Then this data will be stored at the memory instead of go through the CPU. Why don't we directly send the data from the I/O devices, such as the disk drive, to the memory? That is the idea of the DMA. Regarding to the computer system architecture, nowadays many of the computing system is not the single process. Mostly during the semester, we are going to talk about the operating system algorithm based on the single CPU process, single processor. Okay, but it is true we have the multi-process or multi-core system. Okay, in the multi-process, that is called sometimes a parallel or tightly coupled system. Okay, we can increase the throughput. What is the throughput? It's the number of output job. Okay, that is the one indicator to judge the performance of the system. Okay, and economic of scale, not always true. The number of the CPU is increased and performance linearly? No, sometimes down because of the complexity. Okay, reliability, maybe. So there are two types